Jumbo, nuclear fusion. To fuse something means to put together. So in nuclear fusion, we're taking smaller nuclei to make larger nuclei. Really the opposite of fission. In fission, we're taking large nuclei and making smaller ones. But when we talk about fusion, we're typically starting with hydrogen and fusing them together to make helium. That should sound familiar because we talked about it in astronomy with stars. So here's deuterium. That's hydrogen 2, and here's tritium. Tri means 3. And they come together, and all of a sudden we make a helium nucleus, just like in a star, a neutron, and the big thing is we make all kinds of energy. So we've gone from 2 small hydrogens. Helium's not big, but it's bigger than hydrogen, and so we've made a larger nucleus. Now these things have positive charges, and from grade 9 science you know that like charges repel. The hydrogen nuclei do not want to get together. So the only way to do that is to force them together under enormous heat and pressure. There are advantages of fusion versus fission. Remember, there are advantages of fission over chemical reactions, but there are also some drawbacks as well. Pound for pound, kilogram for kilogram, you get 20 times as much energy as from fission. Remember, fission already makes a lot of energy. Cheapness is fuel. For fission, you've got to go and find your fuel, whether it's uranium, and got to mine it, and then you got to purify it or enrich it. Here, for fusion, we need things like hydrogen. Well, hydrogen's all around us. It's in our atmosphere. We know it's part of the ocean and water, and it's in the Earth's crust. And we make little, if any, radioactive waste, which is a real positive. But the difficulty is it's very hard to create the conditions that can force the positively charged nuclei together, where the amount of energy it takes to force them together is going to at least be smaller than the amount of energy you get out. You want to get more energy out than in, and that's very hard to do here on the surface of the Earth. The temperatures and pressures required are massive. And in fact, there's no physical material that can handle that high kind of temperature. So instead of having some physical material, it has to be done under force fields. It'd be nice if we could just run out and harness our local sun, but not so easy for our fusion reactor. Examples of nuclear fusion? Well, the stars. And of course, we've just wrapped up a series in astronomy. We know our star has gone roughly halfway through its supply of hydrogen fuel, and roughly in 5 billion years or so, it's going to run out. And of course, that's probably keeping us awake at night, all the stress of that. And just like the fission, nuclear fission had the atomic bomb, nuclear fusion has the H-bomb, the hydrogen bomb, and where you're releasing even nastier amount of energy. And the South Pacific in the 1950s, all kinds of tests were done in places such as the famous Bikini Atoll, where they were detonating these large bombs to see what their impact was. So that's it for fusion. Sticking hydrogen atoms together under enormous heat and pressure and making lots and lots and lots of energy.